This video is sponsored by PCBWay. Last year, I built a series elastic actuator. It worked. It was powerful, fast, and robust. It could measure and control forces, but it was large, complex, and difficult to manufacture. So this time, I tried a different approach. I learned a lot with the first actuator. Series elastic actuators offer important advantages. They can estimate forces, they can control forces, they can absorb impacts, and they can interact safely with the environment. But for my own projects, there was a problem. The actuator was long, it contained many custom parts, and manufacturing multiple units quickly became difficult. This time, I defined a different set of requirements. The new actuator must be simple, compact, easy to integrate in a robot, and still provide fast response, backdrivability, serial compliance, and force measurement. The actuator must fit in a human arm or leg. I wanted something that could realistically be used in humanoid robots and exoskeletons. The actuator is based in a 6374 brushless motor. Check in my previous video how to remove the shaft of this motor. The ball screw is a model commonly used in 3D printers. You can easily order a custom model with these dimensions. This 3D printed part and a ball bearing will prevent dust from entering the ball screw area. Now we install the ball screw in the rotor. We replace the motor ball bearings with axial bearings. And we can reassemble the motor. In the back part, we put another axial bearing and a clamp. And finally, we use a headless screw to fix the rotor to the ball screw. The output rod is made of a 25mm tube. We use these slots to fix the tube to the ball nut. This aluminum part will prevent the ball nut from rotating. Two small ball bearings will help the ball nut sliding back and forth. We will continue now with the back support of the actuator. A 3D printed part will help supporting the magnetic encoder. We will complete the back assembly with some laser cut parts that I ordered to PCBWay. PCBWay is an online service for your machining needs, providing CNC machining, 3D printing, sheet metal fabrication, injection molding, laser cutting, and of course PCB making services. After uploading my files to the PCBWay site, I could choose the materials and I got a quote almost instantly. Head on over to PCBWay and take a look at their services to see what's best for your projects. You can check out PCBWay today by going to the link in my description. We add some barrel nuts that will be used later to fix the cover of the actuator. And we glue an encoder magnet to the shaft before fully assembling the back part. And we finally assemble the back part. The motor cover is made of a large aluminum tube. We use the barrel nuts to fix it. The ball screw cover is a 3D printed part. The ball bearings installed in the ball nut will slide along these slots in the 3D printed part. Some nuts inserted in the PLA will help fixing this part. Finally, we install a pneumatic actuator rod end. With this, the basic version of the actuator is complete. It measures 27 centimeters and it weighs 1.5 kilograms. Now let's build the elastic part and the force measurement part. The elastic part is based on die springs, which can be found with different stiffnesses. We assemble the springs together with a radial bearing and this 3D printed part. The 3D printed part will be used to move the potentiometer that measures the force. A second spring is inserted in the output tube. And a second radial bearing is also inserted to allow a rotary motion of the rod end. Now we will insert the output assembly. The 3D printed part will protrude through this slot. Now we can tighten the whole assembly. We will use a linear potentiometer to measure the compression of the springs, that is, to measure the forces. I used a 3D printed box to hold the potentiometer in its position. And finally, we close the output assembly. Now the series elastic version of the actuator is complete. It weighs 1.6 kilograms and it measures 33 centimeters. Now let's test a force control algorithm. The actuator can behave as a spring with configurable stiffnesses. Now let's test it with a lever that multiplies the force by 10. The actuator destroyed my test setup, so I decided to test it with my own weight. It can lift up to 300 kilograms.